Weather is the state of the atmosphere describing, for example, the degree to which it is hot or cold, wet or dry, calm or stormy, clear or cloudy. On Earth, most weather phenomena occur in the lowest level of the planet's atmosphere, the troposphere, just below the stratosphere. Weather refers to day-to-day temperature and precipitation activity, whereas climate is the term for the averaging of atmospheric conditions over longer periods of time. When used without qualification, weather is generally understood to mean the weather of Earth. Weather is driven by air pressure, temperature, and moisture differences between one place and another. These differences can occur due to the sun's angle at any particular spot, which varies with latitude. The strong temperature contrast between polar and tropical air gives rise to the largest scale atmospheric circulations: the Hadley cell, the Ferrel cell, the polar cell, and the jet stream. Weather systems in the middle latitudes, such as the extratropical cyclones, are caused by instabilities of the jet stream flow. Because Earth's axis is tilted relative to its orbital plane, called the ecliptic, sunlight is incident at different angles at different times of the year. On Earth's surface, temperatures usually range 40 degrees Celsius, negative 40 Fahrenheit to 104 Fahrenheit annually. Over thousands of years, changes in Earth's orbit can affect the amount and distribution of solar energy received by Earth, thus influencing long-term climate and global climate change. Surface temperature differences in turn cause pressure differences. Higher altitudes are cooler than lower altitudes, as most atmospheric heating is due to contact with the Earth's surface, while radiative losses to space are mostly constant. Weather forecasting is the application of science and technology to predict the state of the atmosphere for a future time and a given location. Earth's weather system is a chaotic system. As a result, small changes to one part of the system can grow to have large effects on the system as a whole. Human attempts to control the weather have occurred throughout history, and there is evidence that human activities such as agriculture and industry have modified weather patterns. Studying how the weather works on other planets has been helpful in understanding how weather works on Earth. A famous landmark in the solar system, Jupiter's Great Red Spot, is an anticyclonic storm known to have existed for at least 300 years. However, the weather is not limited to planetary bodies. A star's corona is constantly being lost to space, creating what is essentially a very thin atmosphere throughout the solar system. The movement of mass ejected from the sun is known as the solar wind. Causes. On Earth, common weather phenomena include wind, cloud, rain, snow, fog, and dust storms. Some more common events include natural disasters such as tornadoes, hurricanes, typhoons, and ice storms. Almost all familiar weather phenomena occur in the troposphere, the lower part of the atmosphere. Weather does occur in the stratosphere and can affect weather lower down in the troposphere, but the exact mechanisms are poorly understood. Weather occurs primarily due to air pressure, temperature, and moisture differences from one place to another. These differences can occur due to the sun angle at any particular spot, which varies by latitude in the tropics. In other words, the farther from the tropics one lies, the lower the sun angle is, which causes those locations to be cooler due to the spread of the sunlight over a greater surface. The strong temperature contrast between polar and tropical air gives rise to the large-scale atmospheric circulation cells and the jet stream. Weather systems in the mid-latitudes, such as extratropical cyclones, are caused by instabilities of the jet stream flow. Weather systems in the tropics, such as the monsoons or organized thunderstorm systems, are caused by different processes. Because the Earth's axis is tilted relative to its orbital plane, sunlight is incident at different angles at different times of the year. In June, the northern hemisphere is tilted towards the sun, so at any given northern hemisphere latitude, sunlight falls more directly on that spot than in December. This effect causes seasons. Over thousands to hundreds of thousands of years, changes in Earth's orbital parameters affect the amount and distribution of solar energy received by the Earth and influence long-term climate. See Milankovitch cycles. The uneven solar heating, the formation of zones of temperature and moisture gradients, or frontogenesis, can also be due to the weather itself in the form of cloudiness and precipitation. Higher altitudes are typically cooler than lower altitudes, which is the result of higher surface temperature and radiational heating, which produces the adiabatic lapse rate. In some situations, the temperature actually increases with height. This phenomenon is known as an inversion and can cause mountain tops to be warmer than the valleys below. Inversions can lead to the formation of fog and often act as a cap that suppresses thunderstorms development. On local scales, temperature differences can occur because different surfaces, such as oceans, forests, ice sheets, or human-made objects, have differing physical characteristics, such as reflectivity, roughness, or moisture content. Surface temperature differences in turn cause pressure differences. A hot surface warms the air above it, causing it to expand and lower the density and the resulting surface air pressure. The resulting horizontal pressure gradient moves the air from higher to lower pressure regions, creating a wind, and the Earth's rotation then causes deflection of this airflow due to the Coriolis effect. The simplest systems thus formed can then display emergent behavior to produce more complex systems and thus other weather phenomena. Large-scale examples include the Hadley cell, while smaller-scale examples would be coastal breezes. The atmosphere is a chaotic system. As a result, small changes to one part of the system can accumulate and magnify to cause large effects on the system as a whole. This atmospheric instability makes weather forecasting less predictable than tidal waves or eclipses. Although it is difficult to accurately predict weather more than a few days in advance, weather forecasters are continually working to extend this limit through meteorological research and refining current methodologies in weather prediction. However, it is theoretically impossible to make useful day-to-day predictions more than about 2 weeks ahead, imposing an upper limit to potential for improved prediction skill. Shaping the planet Earth. Weather is one of the fundamental processes that shapes the Earth. The process of weathering breaks down the rocks and soils into smaller fragments and then into their constituent substances. During rain's precipitation, the water droplets absorb and dissolve carbon dioxide from the surrounding air. This causes the rainwater to be slightly acidic, which aids the erosive properties of water. The released sediment and chemicals are then free to take part in chemical reactions that can affect the surface further, such as acid rain, and sodium and chloride ions salt, deposited in the sea's oceans. The sediment may reform in time and by geological forces into other rocks and soils. In this way, weather plays a major role in erosion of the surface.